Today we are taking a topic of control system is transient response specification. So there are multiple responses we are going to measure where the transient response specification are most important because ultimately it leads to the analysis of whole response we are getting based on whatever input and output. So looking at the diagram, the actual behavior of the output based on input given unit step. So if you are going to look at to the diagram on a y-axis, we will be having C of t, a transient response, and on x-axis we are having a time. Based on input is step, so you will be getting a straight line at 1. This will be considering is our desired output. In order to getting this particular desired output, we have start giving input at 0 second. So at 0 second, it is going to be start giving input and gradually it is going to be start increasing. Initially, it is having some basic oscillation considering as transient response, and after some time it is going to become steady until it is going to be reached to the steady state. So before it is going to be reached to the steady state, there are multiple oscillations it is going to be passing through considering as a transient response. And ultimately we have to focus on some basic parameter for the analysis purpose which is actually belonging to a transient response. So as you can see some different notations over here, TR, TP, TD, MB, these all are existing into a transient response for the specification and analysis purpose. So let us look at different definition of each individual parameter, starting with the first one called delay time. So according to a technical definition of delay time, it is the time required for the response to reach 50% of the final value in the first attempt. One more time, the important and key parameters over here is what? It has to reach up to the 50% of its final value in the very first attempt. Now let us understand this definition with the help of diagram. Now here you can see our desired output is a transient response for unit step. It is going to be start giving input at 0 second and it is going to be start gradually increase. So whenever it reach up to 0.5 means 50% of its final value. So whatever time taken for the response starting from 0 second to reach up to the 5 second considering as 50% of final value, this much of time known as delay time. So how much of delay actually a control system response will getting to reach up to its final value, and that particular final values time we have to calculate for the very first attempt. It is a mandatory condition to calculate the delay time in the very first attempt. So the very simple definition of a delay time is total time required for response starting from 0 up to the 50% of its final value considered as TD. As you can see TD into a diagram very specifically shown from 0 to 50%. And the equation to calculate a delay time is TD equal to 1 plus zero point 0.7 zeta upon omega n second, where zeta is actually considering is damping ratio and omega n is considering as natural frequency of oscillations. These two particular parameters are most important for second order system analysis. Every time by comparing your characteristic equation with the second order system, we need to find out values of zeta and omega n. Once you will be getting value of zeta and omega n, put down those values over here, you will be getting your delay time in terms of second by using this equation. Similarly, the second most important parameter is called rise time, denoted with TR. Now look at the definition. It is the time required for the response to rise from 10% to 90% of its final value for the overtime system, while from 0 to 100% of its final value for undertime system. So it is again one more time depending upon a different type of system. But the important and key word over here in this definition is to rise. Each particular response of your control system is going to be start rising from one value to another value. So for the delay time, it is going to be reach up to 0 to 550%, while it is going to be start rising from 10 to 90% for the overtime system, while from 0 to its final value of 100% for its undertime system. So total time required for the response to rise from certain value to the certain value. And if you wanted to calculate TR, obviously we have to go with these particular equations. TR equal to pi minus cos inverse theta divided by omega n under root 1 minus theta square, where this cos inverse theta is considering as a value in terms of theta, which is calculated in terms of radian, and omega n is nothing but damping frequency denoted with omega d. So the another equation for the rise time can be written as Tr equal to pi minus theta divided by omega d, where theta is every time comes in terms of radian, which is already given to you, and omega d is nothing but the damping frequency. Third parameter is considering is a peak time. Now, based on its title, we can understand that peak time is nothing but the time required for the response to reach its peak value. So, the peak value of a total response. Let us understand this by using a diagram. So, if we are going to observing this particular whole diagram, which this particular value is considering is a peak value of overall response. So total time required for the response starting from 0 to reach up to its peak value is known as TP. Quite simple. So peak time is nothing but total time required for getting a peak value. So whatever the maximum peak value of the overall response that we need to find out, and based on that how much time required to reach its value considering as TP, and that we are going to be calculating with this equation called TP equal to pi by omega d, and omega d is obviously damping frequency denoted with omega n under root 1 minus zeta square. So TP equal to pi upon omega n under root 1 minus zeta square second. So peak time is also considering in terms of second. Next parameter is peak overshoot denoted as MP. So MP is considering is the largest error between reference input and output during a transient period. Means it is going to be also considering as this is nothing more than a largest error between our actual output and a desired output. So desired output is actually unit step considering as 1, but in order to achieve this particular one value we will be having a different transient response. So this whatever the maximum response or a maximum error you can find out considering is an MP. So MP is directly correlated with the peak time. So at peak time whatever the largest error you will be getting known as MP, maximum peak overshoot, and those peak overshoot can be calculated with this particular equation. MP equal to e raised to minus phi zeta upon under root 1 minus zeta square. But these peak overshoot are always considering in terms of percentage. Means what error is also going to be considered in terms of percentage. And that is why the final equation for MP in terms of percentage is e raised to minus pi zeta upon under root 1 minus zeta multiplied with 100. Once we are going to be multiplying with 100, you will be getting the values of MP in terms of percentage, because error will be error will be considered in terms of percentage. The last parameter is called settling time, denoted at TS. Now settling time means a time required for the response to decrease, because ultimately it is going to be gradually decrease and stay within a very specified percentage of its final value. Means what? This is the total time required for the response to settle down, and once it is going to be settled down, whatever the time is going to be taken with the whole response node denoted as Ts. But when we are going to be calculate settling time, it depending upon how much tolerance band we will be having, depending upon different type of input and depending upon its own output, the total transient response having a different tolerance capacity, which is going to be varying from 2% to 5%. And based on those different values of tolerance band, you will be having a different equation. Let us look at to the diagram for the settling time. Once you are going to see this, it is going to be start gradually increasing from here, and then it is going to be decreasing, and then it is going to be stay within a very specified period of time with a specific tolerance band of 0.02 so over here. Standard is 0.2%, standard is 2%, but it is going to be vary up to 5% depending upon a different input and output. So TS is the time up to here, because after this particular time it is going to be settling down. So there will be no more fluctuation comes over here. So total time required for the response to settle down in a very specific range known as TS. And to calculate TS, we are having an equation TS equal to 4 by zeta omega n, where we are having a tolerance capacity of 2%, and similar way if we are having a tolerance capacity of 5%, the equation would be varying from TS equal to 3 by zeta omega n second. It is extremely important to mention unit at the end of every example when you are going to calculate all these parameters. And finally, it is recommended that after finding out each particular parameter, you need to mention all those values into a given diagram, considering its own values in terms of percentage or second.